Okay, hey guys, good evening. Hope you all can hear me. So let me know in the chat if you can hear me. Today we are at the sixth session in this advanced programming series. So we have started on heaps the last day. I hope I'm clearly audible. Okay, yeah. So we started on heaps the last day, and today we are going to continue with heaps. Hi Ayush. We are going to continue with heaps today and then proceed to heap sort as we had discussed towards the end of the previous class. And then we'll be discussing problems around both heaps and heap sort. Okay. The chronology is a bit different. I'll first complete the theory behind heaps. I'll complete it with the implementation details. Then we'll jump into the problems around heaps. Then we'll proceed to heap sort. I'll discuss heap sort which will be quite easy, and then we'll proceed to the problems around heap sort or related topics. Okay. So fine. Uh, any questions you have? We'll be starting soon. We'll be starting at around how much? We'll be starting at 5:37 p.m. 4 minutes away. In the last class, we actually saw a lot of things around heap. I'll be summarizing that, but before that, if you have any questions related to heaps or related to any other topic, you can ask now. About myself, I am Saptarshi Mukherjee. I've graduated from IIT Bhilai this year, having pursued BTech in Computer Science and Engineering, and then I've joined Google. Currently, I'm working there as a software engineer. So, apart from this, I've enjoyed computer programming in my college years. I've been to the ACM ICPC regionals twice, and I've been a 6-star rated coder at CodeChef and a master in code forces. Okay, I'm happy that you liked them because there were some good things I remembered I had discussed. I've taken multiple sessions on segment trees, and every time when I've taken a session, I've deferred it slightly from the previous session. So it happens, it just happens because I don't follow some strict order. So, anyway, here also we'll follow some Heinemann. So, anyway, last day we have started on heaps. Related to heaps or related to any other thing, if you have any questions, do let me know. I'll try to answer it before we start on the topic. So last day what we covered is that is slightly a prerequisite because I'll be discussing the implementation. So if you know slightly, if you have slight idea about how the things happen, Heapify up, Heapify down, then you will find greater interest to follow it. You don't remember, you don't need to remember everything too strongly because it will be a kind of revision. So in the last class we had seen the basics of heap. We discussed what a heap looks like, how it is different from a normal complete binary tree, and then we looked at the heapification process. We looked at the time complexities of building a heap, and yeah, those were the things. How to identify questions on heap. Uh, Great, that is indeed a very pertinent question. So if you remember or if you have attended the previous class or any other class which anybody else has taken, you might have noticed that in a heap we don't stress on, like suppose there's a min heap. In a min heap, we don't dictate whether the left one is going to be greater or the right one is going to be greater. We don't say it can be 5 over here, 3 over here, or it can be exactly the other way. We can have 3 over here and 5 over here. There is no such, strong, strict regulation. But the only thing is that if it is a min heap, then the parent should be smaller than both of them. So it can be 2 or 1 or minus 1, it can be anything. What this means is that if you apply this on every subtree, that the children are always greater than the parent is always smaller. It means that the root of this entire tree is going to be the smallest value, which means that at any different position, at any different situation, when you feel that okay, I have these elements, who has the least value currently? Then you can easily fetch this value and you can say, okay, I'm removing this. Now I need to find out who is the next minimum. To find out the next minimum, you don't have to proceed through the entire path. You can directly say, okay, I will find out from here. I will search over here. I'll search over here. I'll be finding out. I'm sorry. So we don't search. What we do is that when we have to form the heap, when we have to rebuild the heap, we do a single heapification process by which we say that okay, my root is gone, my root has been taken away, so now it is a vacant place. So I will do some heapification. I will swap it with the last node, and then I'll heapify it from the topmost node, which will be a heapification down process. And by that we can easily do the swapping. What this tells us is, suppose you have this kind of a use case. What I'm telling is that new people are coming. At every moment, you have new people who are entering, and there are these kind of queries. Maybe suppose there are queue queries. Okay. At every step, two things can happen. One is somebody is entering. So someone is entering. Suppose it is a query of type 1, and we are giving value. So he is coming with a value of this. And the next query is something like this, just 2. What it means is whoever has the suppose least value, whoever has the least value, he has to be omitted from the heap. If there are 2-3 people who have the least value, then either of them can be omitted. Okay, any of them can be omitted. So what this means is, in this kind of a query, I hope you understand the query. We have something like this. Suppose the sample input is something like this. You have an empty array, there is nothing. I'm entering 5, I'm entering 2, I'm entering 3, I'm entering 4. And then I'm saying, okay, give me the smallest element. Then I tell you, now you enter 6. Now you enter 2.5 maybe. And now tell me the smallest element. In this manner, if we query, suddenly if we query this, what happens is, whenever I face this query, I need these elements in the sorted order, right? Or I need to store which is the smallest element over there. Suppose after this again I would have said that okay, I again want the smallest element. What this means is that after removing the smallest element, I still want to know what is the next smallest element. What this means is that our data structure should have a property that even if the smallest element is removed, you can very fast convey the information that this is the next smallest element. And when a new element comes, it will be very easy to place that element in the correct position. When you think this in terms of an array, that okay, I'll sort the array, I'll first sort the array and then I can easily answer, okay, this is my smallest, this is my second smallest, this is the next one. And now I tell you, okay, now you have to enter 5 elements and then you have to give me the smallest, second smallest and these things. If you have to enter in an array, if you have to enter this, then the problem is that you need to, maybe you can perform some binary search. And after that, the way you do in insertion sort is, you have to come over here, if this is the perfect place, and all these elements you have to shift one place rightward. Do you understand this? You have to shift all the elements one place to the right. In an array, if you have to do this, that okay, I want to enter one element in the perfect place, I want to push everything else to the right. So you have to like consume something which goes to order n. Either you push everything to the right or you push everything which is on the left to the left. Whatever you do, you have to consume order n kind of operation, which essentially tells us that using an array, this kind of an use case is not that feasible. So it is in this use case that we use a heap. So because we have quite many people, I would be starting off with some very basic questions which you must know. Does a heap give us the elements in sorted order? Give us means that suppose this is a heap, so I'll read it in some manner. Maybe this is the heap, so I will tell you, okay, either read in this manner, this manner, this manner, this manner. I'll get all the elements in sorted order, or maybe it can be even the other way. So is there some way by which I can always get all the elements in sorted order? Give us all elements in sorted order. Is there any technique like does a heap, if I ask a heap that give me the 5th smallest element, can it directly give me the 5th smallest element? Can we relate heap with some real life examples? Definitely. Suppose think of your operating system. Let me know if it is too technical. What happens is, for every process, there is a kind of marker that what is the priority. Along with that, for every process, pre-order traversal. Interesting, I'll come to this. But what OS does is, for every process, there is kind of some priority assigned. So whenever scheduling is done, there are some scheduling algorithms which observes this priority, and they also see how long this process is waiting. So suppose I figure out this kind of an algorithm. Um, you can think it in that kind of an algorithm which we do for scheduling processes, that whichever process is waiting for the longest time, I should schedule that one. I should schedule that, and after that, when it finishes, I will then check that out of all the processes which have entered, or which anyway, so I want to see which has waited for the longest amount of time. Think like any traffic system. If traffic system is made automated, if it is ever made automated, what shall happen? In a traffic like automated traffic system, you want to do something like this, that wherever different roads are meeting, you want to automate the traffic signal so that wherever you find greater number of cars, greater congestion, you want to allow those cars to cross. So something should be monitoring that whatever new cars are coming, it will always keep on monitoring that, okay, this car has come at this point of time. Or you can say there are 5 different roads at a certain junction. There are 5 different roads. We don't know which one to give the signal at which amount of time. So when we know the cumulative value of the cars who are waiting, maybe the cumulative waiting times, if we keep a value and then we say that, okay, whoever has waited the most, we will allow that direction to start moving. You can think it in your own manner. Got it. So actually, too many questions have passed. I didn't observe that. You can also think of more examples. But yeah, the question is, does a heap give us all the elements in sorted order? Let me look at the answers. So do sets and priority queues use heap internally? Yes, sets does not use. Set has a very different way of working. C++ set has a very different way of working. So set does not use, but yes, priority queue uses. Priority queue uses a heap internally. Then coming to the next thing, hash set doesn't, reset does. No, tree set doesn't use a heap. Tree set uses a red black tree. Set, tree set, these things, whatever you call, they use a red black tree. Basically balanced binary search tree, BBST. They don't use a heap. So you can delete any element, you can fetch any element in order log n time. But a heap will never tell you that, okay, you want an element, I can search you in log n time. So that is a basic difference from this set kind of data structure and heap. Okay. Tree set doesn't use heap. No. Tree set doesn't use heap. So the next is okay, similar to pre-order traversal. Pre-order traversal, the problem is that you don't know it. Suppose we have something like this. Anyway, you have to cover the entire thing. You have to come over here, then come over here, then you have to come over here, then come over here. You have to cover the entire thing, which means order n time. But when we are asking about like in the sorted order, what do we want? That it will give me the elements. After this, I want the smallest element. I'll find the smallest element here. Then I don't know which of these is the smallest. Suppose I find it by a single comparison that this is the smaller of these two. Then I'll say that which is the second, which is the third smallest, which is the third element. It can be this guy, it can be this guy, it can be this guy. Can you see that it is expanding? Now there are 3 choices. All of these are capable of being the third smallest element. So a heap does not give us, the answer over here is no. If you have any questions around this, please ask. Let's say if we want top 100 rank of student of any exam, we can use min-heap, right? Top 100 rank of student. Are you asking like we want that student who has the 100th rank in a class of 500? Are you asking something like that? That I want the student in one operation maybe. I want the student who has a rank of 100 in a class of 500. If that is the case, then the answer is no. We can't readily find out who is the 100th rank element. We can't find out. Okay. Okay, if you want something like this, or okay, I want the first rank, the second rank, the third rank, the fourth rank, everything we want, then that is a different step. First, we can find out who has the first rank. We know that that guy is at the root. If we remove that root, if we say that okay, we will remove the best student, the rank 1 student, then the rank 2 student will appear at the root. By heapification, it will come at the root. We can say okay, this is the element which is actually which deserves to be the best currently, and hence it is rank 2. Makes sense? All 100, got it. All 100 means it is something like this. Suppose, let me show a very proper example. Suppose we have this kind of a heap. Where I have these elements 1, 2, 5, 8, 9, 10, 11, and we have something like this 1, 5, 2, and then I have something like this, or maybe that's not 5. We can have 10 over here, I believe, 2, and below 2 we can have, I'm sorry, so we can have suppose 9 over here, we have 2 over here, we have 5 and 8, and over here I have 10 and 11. Does this look fine? Is this a proper heap? So now I'm interested in finding that what are the ranks of these, like suppose these are objects. These are objects with values like this. So I want to find out, okay, what is the value of the first guy? What is the value of the second guy? In this manner I want to find. So it should present me exactly in this order. I want this as the output. So can you see that this is a proper heap? A proper min heap? No. Why no? Tanu? What is the property of a min heap? Min heap has only one, what can we say? Yeah, it's a complete binary tree, and the parent should always be less than equal to the children. Can you see that the parent over here is less than equal to the children? 1 is less than both of them. 9 is less than both of them. 2 is less than both of them. Can you see this? So this property, if this property that parent is less than the children, parent's value is less than the any child's value in terms of value, then we say that okay, heap property, min heap property is maintained, right? Yeah. So this is a proper heap. It does not require to be that okay, you must have 2 over here, you must have 5 over here. No, a heap does not dictate this. You can have any set of values, it should just obey this property. So now after this, if suppose I ask, does it have to be complete? Yes, it must be complete in the sense complete binary tree means if the last level is not complete, then they should be they should be concentrated towards the left. If the last level is not complete, suppose there are 8 spaces in the last level and you have only 5 nodes to fill up, so you should cover the leftmost 5 nodes. Okay, the entire heap should follow the property of heap, this property. Okay, so I'll tell you how it basically works. How do we ensure heap is balanced? Okay, because heap is a complete binary tree. Heap is a complete binary tree. What is a complete binary tree? A binary tree in which only the last level may be partially filled, but all the other levels are completely filled. So if you have this guarantee that all the other levels, interior levels, are completely filled and only the last level is partially filled, then that is automatically balanced. Got it? Yeah. So over here, suppose I say that okay, I want the least element. You can tell okay, we have 1. There you are. We have 1. It will tell you. Now I'll say okay, I want the second smallest element. What should we do? The heap internally shall, like we can say that okay, remove the first element. I want the second element. There is no internal mechanism to tell us which is the second element. Take my word, believe me, like there is no internal mechanism. Over here, if I ask which is the 4th element, without changing the structure of the heap, nobody can say who is the 4th element. Okay, the 4th element is 8, but without changing the structure of the heap, nobody can say who is the 4th element. Heap does not have this property. No implementation can have this property. If it does have, then it is not optimized. So heap by definition does not serve this requirement. But what we can say is, we can say that okay, you want the second element, so let us remove the first element and then ask who is the best element now. If we want the 4th element, we will say remove the top 3 elements and then ask who is the best element now. So this is how we do it. So if we want the ith element, If you want the ith element, we say that okay, remove the first I minus 1 elements, remove the first I minus 1 elements. Today we can stretch the class if you don't have any problem, because I think we'll require more time. So we will remove the first I minus 1 elements, and then we will say that okay, now find the smallest element. Find smallest element. Whichever is the smallest element, that will be our answer. Make sense? Start from root and go to the next small element and print the elements. No, Jeevan, there is a problem with it. Let me tell you what is the problem. Suppose you're over here, you tell the okay, this is the smallest element. Then you say that okay, over here I have the best element. So you have said that okay, this is of rank 1, this is of rank 2. Now where can the third element be? Third element can be over here or over here or over here. These are the only 3 places. Suppose, let's say this is the place, this is the third element. So we mark this as third. Now which can be the fourth element? Can you see that there are 4 candidates for the fourth element? There are 4 candidates over here for this fourth element. What does this mean? Let us take another example. Now I've seen that okay, this is a fourth element. What does this mean? Now what can be the fifth element? This guy can be the fifth element, this guy can be the fifth element, this guy, and this guy. There are 5 candidates, which means we have to compare all the 5 elements. We have to compare all the 5 elements that okay, if A is less than B, then compare A and C, else compare B and C. Whichever comes lesser, compare that with D. Whichever comes lesser, compare that with E. This kind of thing we have to do, which is pretty non-optimal, you can say. At the end, it will like involve n by 2 nodes maybe. So one query operation that which is the kth element will actually request you to cover k comparisons, which is pretty inefficient. So what do? We adopt this kind of a technique. Why? The precise answer to this is, had it been an offline class, I would have asked you why. Why do we adopt this kind of a technique? Because removal is fast. If you have to remove the best element, that is a fast operation. Removal from a heap happens in order log n time. Okay? So if you have to remove the first I minus 1 elements, in order log n times I minus 1 time, I can remove all those elements. Right? And then if I have to find the smallest element, this also happens. This happens in order 1 time. I know whichever is at the root, that is the best. Got it? Right. It might occur anywhere, and finding him is cumbersome. Right. So are you getting this? I'm not removing all the elements together. I'm removing them one by one. Each one will take log n time. Hence, it is I into log n, you can say. Now you can ask, okay, it is still order I or more than order I. So where have we bettered? In this case, what shall we have? If we have to remove the first element, it is order 1 step. If the second element, I have to compare 2 elements. Third element, I have to compare 3 elements. So if you do this 1 plus 2 plus 3 plus 4 plus all these things, what shall you get? Something like order n square. Can I say order I square? So can you see that we have bettered from order I square to order I log n? Is this part convincing? That using heap, we have at least bettered it from order I square to order I log n by that removal process. What I've just said is that if you want the ith element, remove the top I minus 1 elements, and then you can get the ith rank element. And now what we can do is, we can collectively say if we want the best, if we want the top 100 rank elements, that which you mentioned, what will I say? Initially we have this heap. So now we will say this is the best element, done. Then we will heapify this. We will convert the remaining elements into a heap. We will remove this and we will convert this into a heap. This will take log n time. Then we will say, okay, which is the best? Now this is the best. So this is of rank 2. Then we will remove this. Then we will say, which is the best now? This is the best now. So we will say this is of rank 3. So in this manner, all the ranks will be getting. And each of this removal will happen in log n time. And every time when you will go to find the min element, new min element, it will be an order 1 operation. So can you see that there is a very optimized operation? Okay. Ordering concept. Let me take this example. 1, 9, 2, 11, 10, 5, 8. This should be clear. We can't stretch it beyond this. 1, 9, 2, 11, 10, 5, 8. I think we had something like this. Now what will we say? We will say we want the best element is 1 at the root. So we will say, okay, we have got 1, now we will convert it. We'll convert it to something like this. We will have, like, this will get removed, and then what shall we have? We'll have a vacant over here, we'll have other things like this, and then what shall we say? Okay, let's place this 8 over here. This is heapification, like not heapification, this like swapping it. We'll say now this node no longer needs to exist, we can place 8 over here. We have 9 over here, 2 over here, 11 over here, 10 over here, 5 over here. These are the nodes. Now this is not like, this does not follow the property of the heap. And vice versa, let's say if you want to sort according to highest marks, then we can do max heap, which satisfies a condition that parent should be greater than child, right? Exactly. Highest marks, exactly. So there we will actually use a max heap. Okay, so is there anyone who has a problem with Hindi? Is there anyone who has a problem with Hindi? Or is everyone fine with Hindi? Is everyone fine with Hindi? No problem. Vivek Pandey, can you clarify, like no means no problem, or okay, fine with Hindi, great. So okay, I'll continue in bilingual manner now. हम क्या कर रहे हैं, हमें निकालना है कि टॉप 100 लोगों का जो स्कोर्स है, ऐसा कुछ निकालना है कि बहुत सारे लोग हैं और स्ट्रीम में से आ रहे हैं, तो किसी कुछ टाइप का लाइक यूज केस है, और हमें बताना कि हु इज़ द टॉप नाउ, हु इज़ द सेकंड टॉपेस्ट एंड सो ऑन, इस तरीके से कुछ. तो हम क्या बोल रहे हैं इधर कि अगर हमें निकालना है कि हु इज़ द फिफ्थ, अगर हमें फिफ्थ बंदे को निकालना है, हम क्या बोलेंगे कि पहले 4 को निकाल दो. कैसे निकालेंगे? समथिंग लाइक दिस, कि पहले को पहले धक्का मार के निकाल दो. पहले को निकालने का टाइम कम्प्लेक्सिटी ऑर्डर लॉग एन. पहले को आप निकालना चाहते हैं तो ऑर्डर लॉग एन. वो क्यों है? क्योंकि ये कुछ ऐसा होगा, देखते इधर 1 को हम निकालेंगे, फिर क्या होगा, हम क्या करते हैं 8 के साथ लास्ट जो नोड होते हैं उसके साथ स्वैप करते हैं. क्यों? क्योंकि ये नंबर ऑफ नोड्स 1 से घट जाएगा, तो इसलिए हम लास्ट नोड को इधर से हटा देते हैं. फिर हम क्या बोलते हैं कि अच्छा अब तो ये हीपीफाइड नहीं है, क्योंकि ये 8 जो है ये अपने चाइल्ड से बड़ा है, दिस इज ग्रेटर देन इट्स चाइल्ड. सो व्हाट वी से इज दैट ओके स्वैप दिस, जो भी दोनों चिल्ड्रन में से जो भी छोटा है उसके साथ स्वैप कर दो. तो इस समय क्या मिलता है, समथिंग लाइक दिस, वी हैव 2 ओवर हियर, वी हैव 9 ओवर हियर, वी हैव 8 over here, I'm sorry, yeah, it's fine. Then we have the same thing, 11 and 10, and then we have 5 over here. फिर हम क्या बोलते हैं कि इधर हमारा 8 है, इधर हमारा 5 है. हमने इसको तो ठीक कर दिया, इस पार्ट को हमने सही कर दिया, बट अब नीचे वाला पार्ट फंस गया, नीचे वाला पार्ट अब हीपिफाइड नहीं है. तो हम बोलते हैं अब इन दोनों को स्वैप करो. इन दोनों को स्वैप करने से ऐसा कुछ मिल जाता है, वी गेट 2, 9, 8, I'm sorry, we have 5, we have 8, we have 11, we have 10, right? तो अब ये परफेक्ट एक हीप है. नाउ दिस इज अ परफेक्ट हीप. सो व्हाट हैव वी डन? यहाँ पे लॉग एन टाइम ऑपरेशन मैं क्यों बोल रहा हूँ, क्योंकि हमने इधर बेसिकली इस एलिमेंट को हमने रिप्लेस किया, दिस इज अ न्यू एलिमेंट. नाउ इसको हम नीचे तक ले आ रहे हैं, जहाँ तक इसको लाना पड़ेगा. हमने पहले नीचे वाले लेवल में लाया, फिर इसको इधर से नीचे वाले लेवल में लाया. दिस इज व्हाट वी आर डूइंग. और ये सॉर्ट ऑफ, ये मैं पिछले दिन काफ़ी डिटेल में एक्सप्लेन किया था कि इसके एज अ रिजल्ट ऑफ दिस, व्हाई इज द फाइनल हीप लाइक अ प्रॉपर हीप, व्हाई डज द फाइनल हीप गेट्स बिल्ट इन द प्रॉपर मैनर. इसमें आप अगर देखेंगे तो हमने 1 हटा दिया और बाकी जो एलिमेंट्स है वो एक प्रॉपर हीप में है. सो आपका स्मॉलेस्ट एलिमेंट आपके रूट में आ गया. कैन यू सी दिस? ये आपको उधर जल्दी से नहीं मिल रहा था कि विच इज़ द स्मॉलेस्ट एलिमेंट, बट इधर ऐसे आ गया, या सेकंड थर्ड स्मॉलेस्ट एलिमेंट और फोर्थ स्मॉलेस्ट. बट यहाँ ये पूरा एक प्रॉपर हीप टाइप का बन गया, जिससे आपका स्मॉलेस्ट एलिमेंट एकदम ऊपर आ गया. अब आपको बस पूछना पड़ेगा कि इफ़ यू जस्ट वांट द सेकंड स्मॉलेस्ट एलिमेंट in this total structure, you just have to remove the first element, it will get heapified. Then you have to ask for the new smallest element. Got it? Now this is the second smallest element. अब हम क्या बोलेंगे, अब हमें चाहिए the third smallest. थर्ड स्मॉलेस्ट अगर चाहिए तो कुछ ऐसा होगा, यहाँ से हटाता हूँ. Heap contains duplicate as well, right, or only unique? It depends on the implementation, it depends on the library that you are using. But in case, ये क्वेश्चन पिछले दिन भी आया था, इन केस आपको चाहिए कि दोनों AI और AJ सेम है, AI और AJ they are the same in value, you can store in this manner, AI, I and AJ, J. और उसको आप कंपैरेटर के बेसिस पे कुछ सॉर्टिंग लगा सकते हैं कि ठीक है AI लाइक पहले के बेसिस पे सॉर्ट करो और फिर सेकंड के बेसिस पे, जैसे C++ का पेयर सॉर्ट होता है. तो उस केस में क्या हो जाएगा, हमेशा दे विल ऑक्यूपाई डिस्टिंक्ट पोजीशंस. यू कैन कीप इन दिस मैनर. गॉट इट? ओके, इंग्लिश. फाइन. So I'll keep in both the languages, and whatever I speak in Hindi, I'll be speaking in English as well. Okay? But I hope you have understood till now. So we are getting the second smallest element. Now what we'll do, we will say that okay, to find the third smallest element, we will delete the second smallest element. So how shall we delete? We will say that okay, remove this. Removing this means 8 will come over here. So 8 you have over here. This is how it looks like. 8, 9, 5, 11, 10. Now what can we say? That okay, 8 here proper, like this is not at the proper position. 8 is less than 9, that is fine, but 8 is greater than 5. So let us swap this. When we swap this, it is heapified. Now you see it is 5, 8, 9, 11, 10. So now you can say that okay, whatever I have in the top, that is my third smallest element. Then you will say that okay, I want to remove 5. You want to remove 5, so what will you do? You have some this kind of a structure. If you remove 5, you will have like you will swap with 10. You'll have this kind of a structure: 10, 9, 8. I'm sorry, 8, 11. So now you will heapify it. You will bring 10 over here. You will bring 8 over here. You will get 8 at the top. So can you see how we are doing it? Now if you ask questions like how is it guaranteed that always the minimum element will come to the top? For this you should understand that the second minimum element must be at the level 1. In the level 0 you have the root. In level 1 the second minimum element must be present. Why? You can think about it. If you don't place the second minimum element in that level, in level 1, basically this level, if you don't place the second minimum element in this level, you can't place it anywhere else. It will break the heap property. So that is the reason. So gradually this is how actually heap gives us whatever we require. Sir, for each node heap take order log n to heapify. So for n nodes it should be n log n. Every node we will not be heapifying. We will not be heapifying every node. So in case you have not attended the previous class, what we do is something like this. What if you have forgotten anything from the previous class? What we say is that if I into, we actually check whether the left child exists or not. So it is not for, it is basically while. So while, what if we need to reuse the deleted element? That is a problem. So we don't use in such cases where we have to remember also. So if you have to just think like this, that okay, I want the 100th element, then I want the 5th element, then I want any kind of element, it is not meant for that purpose. So yeah, it is not actually meant for ranking. Heap is never meant for ranking. Heap, we will look into the questions. Heap is meant for those situations where we say that okay, we want only the best element. Now we have removed some elements, we have added some elements. Again I'm asking what is the best element. Now I've again created changes. Now I ask you what is the best element. So there are many questions which has come earlier. Okay. So anyway, I'll not go into the code. I'll go into the code right away in some website. Why we don't heap? Why it is not order n log n? Can anybody answer? I think I partially answered it. It is because we don't heapify at all the nodes. What we do is We start heapifying at the root. This is heapify down. We start heapifying over here. It will swap itself with exactly one node. If it swaps, suppose with this guy, what this means is this part is totally fine. We don't have to make any changes in it. This part is totally fine. So we won't do heapify over here. So we will do heapify only at this node. If we suppose swap it with this element, then we will do heapify only over here. We may need to do. And this part is totally fine. Only this part will need heapification. Got it? So this is a kind of binary search. In binary search, you say that okay, only look in the left, don't look at the right. And why it is so over here? Because it is in the proper heap manner. Okay. What is rank? By rank, what we basically meant is which is the smallest element or largest element, something like that. Nothing so technical. Okay. I think if you have any other questions, you can ask. Just a second. Yeah, if you have any other questions, please do ask. So this was not actually a part of the schedule, the explanation that we covered just now. Okay, so let us proceed to the implementation. I'll not do the implementation myself. Let's save some time. I think heap implementation. Yeah, C++. We should get something over here. Yeah. So usually what I used to do is whatever code I used to write, I used to ask whether anybody has any doubt in that. But yeah, over here I can basically copy this. So yeah, the code is going to be from this website. It is not going to be my code. So there is no, I think, no possibility of infringement of copyright. You can ask me using the line number. Okay, I am pasting it in my editor so that you can ask directly from the line number. Let's take previous example. If you want 100 rank of the student using Min-heap, 100 rank of the student, 100 rank. What do you mean by 100 rank? It is a bit weird to follow. What do you exactly mean by 100 rank? Did I create it somewhere? Anyway, top 100. Let's say okay. A Max-heap is a heap where the value of each parent is greater than or equal to the values of its children. Which of the following is a Max-heap? Okay, you give some options. Okay, fine. And let me read the next question. Before that, let me first print it. Yeah, CD CP files maybe. I hope you can see the screen, and I hope it is, or maybe I can increase the font. Yeah, CD CP files. Maybe something like this. LCP files, right? Computer programming. LCP files we have over here. Okay, I think I have this. So yeah, this is the same program. So we'll be covering this. Yeah, you can have a look at this. I think we don't require this. Yeah, there we go. So top 100. Let's say if we want top n elements. So for each rank, it will take order log n. So for n element also order log n. Yes, absolutely fine, absolutely correct. For every element order log n, but we won't cover all the n elements. And okay, if you ask something like this, that 100 elements, we want 100 elements, so it should be 100 log n. Yes, the answer is correct. It should be 100 log n. Definitely. if you want them in that rank wise, then what will you have? You'll have n log n. So it is the same thing the way you used to do in merge sort. You used to get something in n log n. It is absolutely the same thing. No difference. Got it? So yeah, for all of them you will require log n time. So it is 100 log n or n log n, whatever. Okay, coming back to this. Any doubts, or maybe we can proceed through the code. So that's basically what a heap is initialized with. We say that a heap size initially is 0, which means that currently there are 0 elements in the heap, and this is the capacity. Using some known number, we are actually defining the capacity. This is the maximum number of elements that the heap can hold, and this is the array which we are making. So we are actually building this heap in the form of an array. Please feel free to ask any kind of doubts. Okay, using just a line number, just shoot the doubts. Okay. Now let's see what the different functions are. Insert key. We have to insert a new element. So if it is equal to the capacity, if the size is equal to capacity, then say that it is overflow. Okay. Otherwise, if it is an overflow, then return it. Else, what shall we do? We will say that okay, add the heap size. You can, like, I would have done it differently. I would have said that heap size plus plus should happen later on, and whatever is the heap size over there, we will be keeping this element k. What is this k? The element that you have to enter. Okay, so you have to insert this. So where are we keeping this? We are keeping this in the last index. In the last index, heap size -1. We are keeping this. So essentially, it's something like this. You have, like, this is a heap. Suppose this is a heap, and then we say that we want to insert an element. It will say that okay, insert over here, insert over here. Now we will heapify from over here. How will we do it? Let's see. I think we can swap things. Yeah. How do we do it? We do something like this. That while I is not equal to 0 and the parent's value is greater than my value, we are trying to do a min heap, right? So if we see that the parent's value is greater than current value, then we will swap it. We are swapping the parent and the current thing. And then we are saying that okay, now move to the parent. So what will we say? That okay, if it is not equal to 0, not equal to 0 means it is not the root. If it is root, then it is basically 0. This is basically 0. So if it is not the root, what it will say? That okay, look at your parent and see who is greater. If you are greater, then please swap yours. I'm sorry. If you are smaller, then please swap yourself with your parent. Similarly, you will go along in this manner. Got it? This is how we will be proceeding, only towards the parent. First this was I and this was the parent of I. Then we said this will become I and this will become the parent of I. Where did we say this? We said this over here. I is equal to parent of I. This is where we said that okay, you have swapped yourself with the parent. So now within your subtree or within your parent subtree, everything is fine. The order is perfect. But your parent may not be comfortable with his parent. So go there and manage that. So that is what we are doing over here. If you have any doubts, please do ask. But if you have any doubts with the theory, why we are doing this, then I would rather recommend you to look at the, the previous video, the class we had day before yesterday. You have the recording, like it's YouTube only. But over here, I'm explaining the implementation. So regarding any C++ syntax, anything that you have any doubt, you can ask right over here. This should be exactly the same thing that we discussed that. So if you have any doubts, please throw that. We are just inserting an element, and by this we are ensuring that the min heap property gets fixed, which means that you have a proper heap after this line 76. You should have a proper heap. Got it? Now let's proceed. Let's see what are the other things we are doing. When we have to extract the minimum element, extract means we have to remove the minimum element. The operation that I was showing you, removal takes place in log n time. So let us see how that takes place. If there is nothing, then okay, return int max means there is nothing in the heap. Then if you see that there is only one element, then what can you do? That okay, return it and then just reduce the heap size. You don't have to bring anything else to the root because there is nothing else. Only one element is there. But if there are other things, then it is your responsibility to now form the heap in the new structured manner, so that now the elements take their proper positions. This is what we will be doing. We will say exactly what I had done over there. Whatever I had done over here, exactly this you'll be doing. From here you will say that okay, exchange with this, exchange with this. Let us look at this thing. Maybe over here I exchange this with 8, and then what I said is swap this with 5. Then you could have swapped it with a lower element had it been present. So what are we doing over here? We are saying HARR 0 is equal to I see, Min-heapify function is getting called. So first we are forming this. Now this is not a perfect heap. This thing is not a perfect heap. So we are telling okay, perform a Min-heapify operation from the root. So that is what we will be doing. I think it is there somewhere. Min-heapify function. This is the Min-heapify function where it says that okay, at the root I have got my value changed. So from me, go downwards and see whether my children are comfortable with me or not. If my children are comfortable, their grandchildren were already comfortable with them, so I have no other tension. You can break the process right over there. Got it? So this is what we will be doing. That find out the left and right. These are simple things. Simple things, that which is the left node, which is the left child, and which is the right child. Then we will say int smallest equal to I, and then we will say that okay, if the left child is smaller in value, then take that into smallest. If the right child is even smaller, then take that into smallest. Got it? So whichever is the smallest among the root, the left child and the right child, we are getting that in these lines. Whichever is the smallest value, जो भी इन तीनों में smallest value है, रूट, लेफ्ट और राइट. फिर हम बोल रहे हैं कि ये स्मॉलेस्ट अगर रूट के साथ इक्वल नहीं होगा तो स्वैप कर दो और मीन हीपिफाई कर दो. If the smallest is not equal to I, then swap it and do a min-heapify operation. So any doubts you can ask. Min-heapify operation means you are telling that go to that child, I have swapped myself with that, so now that may have got disturbed, so go from that and see if below that you require some changes or not. Okay, that is what we are doing. So any doubts? We'll be moving to the problems right after this. Before that, if you have any doubts, you can ask. Okay, what else do we have? We have delete key. For delete key, what do we say? If we have to delete a particular index, we will do something like this. We will decrease it by int minimum. So what have we done over here? If you have to delete a particular key when the index is given, what we'll say is that change its value to the minimum integer. So after that, if a heapification takes place, if the value is changed to the minimum integer and then you do heapification, that will come to the root, that will come to the exact root, and then what shall we say? That from that root, if we extract the minimum, that element will get cancelled, that element will get deleted, right? So over here we have given the index, we have not given the value. This is an important thing. Given a value, you cannot suddenly go to a certain position and find out that okay, this is the position and these are the children and those things. You can't find out. Given a value, you cannot find out, but given an index, you can always go to that particular position of the array because your implementation is array based. Alright? Okay, now we are left with one thing. What is decrease key? Decrease key, I actually discussed it last day. If we have to decrease the value of a particular node, so a certain student has maybe a patience power of something. Patience power means he can wait for 10 seconds, or maybe a process in an operating system, it can wait for 5 seconds. And now suddenly it says that okay, I've got my alternative, I can wait for another 10 seconds. So it needs to be updated somewhere. On the other hand, maybe some process had been allotted 15 seconds, but now some emergency has arisen and it will say okay, I can't wait for so long, decrease my time by 5 seconds. So these are things that can occur, these are certain instances that can come. When you have to decrease a particular element within a heap, you also have to reposition that element. Okay, so what are you giving over here? You are giving the index where you have to change the value. Then you are giving this value where it is taken for granted that the new value is less than the current value. Okay, since the function is decrease key. So now that you have decreased it, what will happen? Your children will not have any problem with you, right? Because if you were already less than the children, after decreasing your value, you are still less than the children. I'll come to your question, Abhishek. Let me just finish over here. So, if before decreasing the value, your children were fine with you, that means your value was less than the values of the children. Now that you have decreased your value is still less than the value of the children. It has to be, because you have decreased it even further. What this essentially means is that as you decrease the value, your children have no problem, but your parents may have a problem. Because you are decreasing it, it may happen that you have decreased it beyond your parents. Your parents are supposed to be smaller than you. You have decreased it even behind that. So hence it will be a heapify up operation. You have to go upwards. So let us see how it does it. Again, that kind of a calculation. I equals to parent I. Can you see the same thing that we did in which one? Insertion. The same thing that we did in insertion. The same thing we are doing over here. After decreasing, what we are telling is that run from this node up to the parent and continue this up to the root, so long as you keep on finding that your parent is greater than you. Got it? Okay, what is the time complexity when I try to arrange the heap data in decreasing order? N log n. Fetch all the elements one by one. That is the best you can do. Okay? It has to be, because sorting cannot be done in less than order n log n time. Unless you use something like counting sort or radix sort, it cannot be done in better than n log n time. What that essentially means is that your build heap is order n. The heap shall be built in order n time. So if you do the final sorting operation, which is like getting the elements of the heap in the proper sorted order, if you can do this in less than order n log n time, that means you have sorted the array in less than n log n time. Like, rewind this and listen to what I have just said. If you can do this, that means you have broken that very important or standing point, that you cannot sort the array in less than n log n time. If you can do this task in less than n log n time, you can do even that in less than n log n time, which is not possible. So from a heap, if you want the elements in decreasing order or increasing order, you cannot do it in less than n log n time. You have to remove all the elements one by one. That is the only way you can do it. Got it? I have spoken for quite long. If you have any doubts, you can ask. Any doubts? Now this implementation you will not require in your competitive programming. To be honest, you won't require this implementation. I've just shown you. If you have any doubts today, tomorrow, any day, you can ask me questions on it. We'll be then moving to the implementation which we do as competitive programmers in Java and C++. That is what you will be doing. Okay, to be pretty honest about it. And that will not involve all this coding. They will be implemented in a library. We will see how to implement this, like how to use those functions. So they will also say that, okay, if you have to delete an element, if you have to delete some value, they will offer you the API for it. But the deletion operation is order n. You should know this. Deletion operation, after you find the element, it is order log n. But till finding, you can actually consume order n time in searching for it. Got it? So other than all these small things, there is nothing else to remember. You don't need to memorize this code. You will never except your college exams, you will never, nobody will ask you to write these codes. In your interviews, maybe if the interviewer is very skeptical from your explanations that whether you know a heap or not, he may ask you. So those kind of things, this logic part, you can just tally it, or you can clarify with me whatever questions you have. Let me read through the questions. Which is the best way to build a heap? Either building element one after the other, or take an array and implement at one go. Take an array and implement at one go, because if you have to insert elements one after the other, it will actually take how much time? So it is log n. Insertion actually takes log n. So let us see how much time it takes. First time when you enter something, it is log 1, then it is log 2, then it is log 3 dot 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 up to log n, which means that half of the elements are greater than log n by 2, which means half of the elements are greater than or equal to log n by 2, which means if all those half elements if I take, what will I get? N by 2 times log of n by 2, which means this order n log n. But the build tree operation, which I don't know whether it has been done here or not, let us check. Insert, decrease, min-heapify. Okay, over here they have not done it, but it should be done in one go. Build heap operation. But anyway, in practice what we do is one by one, because n log n and n in competitive programming does not make too much of a difference. But I have faced TLE by doing it on whole array while inserting it one after the other works fine. Maybe the implementation was a problem. What you might have tried it, you might have tried something like this. That I'll heapify first over here, then I'll heapify over here, then I'll heapify over here, then I'll heapify over here, then I'll heapify. Is this what you did? First you try start from here, then you do something like this, or maybe in some DFS manner. First this, then this, then this, then this, then come to here, this, something like this. Either of this? Did you do either of this? So the actual implementation is you have to go from the bottom there. This is what you should do first, then you should heapify these nodes, then you should heapify these nodes. So in that way you will get it order n. Okay. Otherwise I need to see your implementation, because yeah, asymptotically and theoretically build heap is order n, and the operation that we have discussed over here, this is n log n, this thing. So they are two different, and this is definitely the better one. Any doubts? Okay, any more questions? Else we can get into the problems. I think 2 more minutes, that's not a big deal. Let's okay, I'll show the Java implementation at 6:30. Till then, you have any problem, any questions? Any line number that you would like to ask, or any particular function that you want me to speak on, or you just want, like, we won't be going into too much of depth because you won't be realizing it, but if you just have in mind, okay, this operation will take how much time, then just throw the question, I'll try to answer that. Okay, this is a use case, how much time will it take? Any question of that sort. Forget about these codes, these are like jargons, you won't require this. Feel free to write down your questions. Meanwhile, I'll write it down. Okay, we'll do it together. Cool, let us begin. So, suppose we want a structure which will act like a heap. I want to implement that fast in Java. So this is the only thing that I need to write. What is the thing that I'll be storing inside this? Suppose it is an integer. So what will I write? Simply something like this. Priority queue. It is a priority queue of integer. PQ equals to new priority queue. Yeah, that's it. This actually tells us that, okay, according to the usual way in which we sort integers, this is going to sort the elements, or basically it is going to compare the elements. Then we can just use the API. These are the things that you get in your priority queue. This is basically a heap. So suppose we add some elements, you can see this is what you get. Add integer e and it returns in boolean. What does this mean? that you can add some integer e, some int data type basically also works here, and then you get the response in boolean, which is not important. It actually, like, if it is a successful thing, then it returns true, otherwise false, something like this. But you don't require it. You can say that okay, pq.add, and then suppose I add 5, and then I can add something like maybe -4, and then we add something like pq.add 3. Okay, so now if I say that okay, I want to print which is the best value, which is the minimum value. This is important to remember that priority queue in Java is a min heap, okay, and in C++ it is a max heap. A small thing that you should remember. Okay, now you want the best element, so let us look at the API. I have written pq dot, so pq dot provides me these things: add all, contains all, okay, equals remove. Okay, so remove is something which tells you what is the okay, remove also takes in its signature the value which you want to remove. We'll look at that later on. Element, where are we? Okay, we have peak. Okay, so this peak will tell us what is the topmost element. You can use this peak. This will tell us what is the topmost element in the heap. So let us try this. Main.java main. You can see it tells us that -4 is the topmost element. Now suppose I say that okay, enter few elements, enter -9, and then you enter 1, and then you enter something like 2. Suppose we do something like this, and then we will again print what is now new peak, what is the new smallest element. So this is what we can get from here. -4 and then -9. Now suppose I say that okay, I want to remove this -9. I don't want this best element to stay now. So what can I say? Something like this: pq dot poll. What will poll do for me? Poll removes the topmost element and it also returns it. So I can also store it in some variable. It returns a value. But okay, now we just want to remove it, so we are not interested in storing what is the minimum value. Now we want to check what is the second minimum value. So we can again peek it over here. So let us see what we get. You see, after I remove -9, I have -4. Now suppose we say that okay, again remove another element and print it. So remove -4 now, because -4 is the best element, so let's remove it. And let's try the rest of the elements. Look at the things that were present. Now we have 1. So can you see that 1 is the next element, which is the smallest? So can you see that it has ordered this? Where are the other episodes of this course? I'm not sure. Maybe you can search using, I don't know, like maybe someone from CodeChef can help if someone is available here. You should get something. There should be a playlist or something like that. I'm not sure. So, but you can search using segment trees, and you can search using the keywords that you have here. Master DSA advanced level, whatever you have in the title, you can search with that. You should be able to get something. But anyway, does it make sense? Can you see that it is working? Can you see that now this addition, this deletion and everything, this is far easier over here? We can enjoy the basic things that we want. Great. Okay. So let us look at a problem. So what have we discussed? These are the things that you need to remember. So later on when you watch this video, these are the only things that you need to remember. This is for your only interview purpose, only for your interviews or interview MCQs, whatever you have. Before interviews you have some coding MCQs or something like that. A build heap operation always takes order n time. You can observe the video, you can read the proof, but the proof is not important. Build heaps takes order n time. uh, for inserting n is equal to the size of the heap, current size of the heap. Okay, inserting an element will take how much time? It takes order log n time. Then if you say that, okay, finding the minimum element, find minimum element, that is the element with the minimum value, that will take order 1 time. Delete the minimum element, delete the minimum element, delete the minimum element will take order log n time. Why? Order 1 time to find out and order log n time to heapify. The next thing is, remind me if I'm missing something. After deletion, what else do we have? Yeah, finding an element by index. Okay, so I want to find an element by index. I will say that, okay, in this part of the array, this index of the array it is located, I want to just read the value. So it will take definitely order 1 time because index is given. If you have to suppose delete an element by index, so the index is given, you have to delete this element, and after deleting, what you are left with, that should be a proper heap. So this will take order log n time. Okay, after this, suppose if you have to find out something like finding an element by value, so I've given you some value and I want you to find out the element which matches with that. This will take order n time, and hence deleting an element by value. So what I mean by deleting an element by value is something like this. Suppose now I say, you can see that 1 is there currently. Now if I say, okay, pq dot remove, and within bracket I provide 1. Okay, now if I say that, okay, now print the best element for me, let's see what this prints. You will see that it will remove, I'm sorry, yeah, you can see it has removed 1. Now it prints 2. So it has removed 1 from here. It does not go to the first index and delete it, because 1 is at index 0. So it is actually deleting the number, but this is order n. This is order n operation. It provides the API, but you should be very careful while using it, because you will be able to use it, you will be able to see that, okay, your program has compiled successfully and it has passed the sample test cases, but in the main test cases it will fail, and it will actually create a difference between being hired and not being hired in a company. Okay, so remove operation by a value is always ordered n. Deleting an element by value, I repeat, finding it will take order n. Heapification after deletion will take order log n. So deleting an element by value is order n. Updating an element by index, any element by index, I am underlining this index, is always log n, whether you increase it or decrease it, but it is not very important. And okay, for this indexing part, definitely whenever you have to do anything by index, you have to make your own implementation, so that is a different problem. So ideally you should target a heap only when these are the tasks. Build heap, you won't require that much. Inserting an element, finding the main element, delete the main element, that's it. These are the only things. Don't like use a heap for these things. Don't use Java priority queue or C++ priority queue when these are your target operations. Okay, don't do this. You may fall in trouble, you may actually overwhelm the time constraints. Is this good enough? I hope it is clear. Any questions around this? Just if you remember this much, later on whatever we discuss, that they are just supplements. Just go into that to refine your understanding. They are not compulsory. Okay. In any language, you will find all these APIs. Whatever I discussed over here, you will find all these APIs. In Java, for insert, I'm not sure about build, but for insert you have add. For main you have peek. For deleting the main you have pull. These are the only three things that you need to be interested in. Okay. Cool. Let us move ahead. If you have any questions, please do ask. Yes, let us move to our first problem. Find kth smallest element in a matrix where every row is sorted in non-decreasing order. I'm not writing that. In increasing order, every row is sorted. Yeah. Find the kth smallest element in that entire matrix. So suppose this is your matrix. You have 3, 4, 8, 10. You have 1, 5, 100, 101. You have 12, 13, 14, 15, and you have 1, 2, 3, 200. And now suppose I ask for k equal to 5. So your answer should be 1, 1, 1, 2, 3, 3. Your answer should be 3. Okay. It can be either this 3 or this 3. I just want the value. Is the question clear? Pretty straightforward question. Is there any doubt regarding the question? Let's think about it. So don't keep in mind that you have to accept the matrix, you have to input the matrix, so that will only take order nm time, n cross m matrix, that will only take order n into m time. Don't keep that in mind. It may be passed to you as a function, like by reference it may be passed to your function. You need to make your function as optimum as possible. So try to do it in as less complexity as you can. We will discuss all the ideas, but I hope the problem statement is clear to you. Now there is another thing which I think I should show you, which is that priority queue does not only take integer, it can take, or suppose you have integer and then you actually want to analyze them in a different way. So you can write, okay, for a comma b, I want it to be analyzed in this manner. A minus, actually this is the usual order. You will see if I write this actually is the usual order. What this says is, if I have A and B, then the difference is A minus B. So let us look over here. This is what we get. Minus 4, minus 9, the same thing. Whatever we got previously, we got the same thing. Now suppose you want to change it. You want to say, okay, the difference should not be seen in this manner. I want it to be absolute. If you want it to be absolute, you can use math.abs, or you can do something like this. A into A minus B into B. B into B. So over here, if you change this, what will happen? The way your comparator works, it actually takes two integers, and this is what it does. It actually compares them. So you can see, you can read this. It compares its two arguments. How will it do it? It will see how the difference is computed. If the difference is less than 0, that means the first element is smaller. If the difference is equal to 0, that means both are the same. If the difference is greater than 0, that means the second element is greater. This is how it does it. So rest everything is the same. So let us say we have done this a square minus b square. What does this mean? That sign has no effect. So now after these three steps, what can you say? pq.peak will not give minus 4. It will give 3. Why? Because now sign is not a factor. A square minus b square, we can see that 3 square minus 4 whole square. Here 3 square is going to win. So there you see. So now 3 has won. Now we can say that okay, after that what are we doing? We are again saying pq.peak. So after we are doing pq.peak, we are getting 1 after adding all these things. We did not have that. We had -9, but now we are having 1 because it sees the absolute value. There is another thing how we can play around with it. We can use pairs. What is pair? Pair is a custom class that I've created. Let me show that. This is basically my pair, which I basically keep on changing. It is similar to the pair you have in C++. Only difference is that I have defined a different compared to. A minus p dot a means if this first one is smaller, then okay, otherwise other one, something like this. You can do something like this, that if a is not equals to p dot a, then return this, otherwise return this. Okay, something like this. So what does this mean? And this is basic comparator. You can design your own comparator, and then you can define your priority queue in this manner. Now your priority queue is going to store pairs, that is user defined objects. Let's say I keep this as it was and I'll make it separately. Okay. So now this shall have pair, maybe pq1, and now we can store pair. I can say that okay, pq1 dot add new pair 1, 2. Next time I say that okay, pq1 dot add, it will be -1, 20. So now I want to see which is at the top. So I'll say pw dot println pq1 dot peak, whatever is at the top, dot a. I'll just see the first value. Okay, I'll read the last line of output that will contain the answer. It is -1. So you can see this one is at the head because here the first value is smaller. That was our comparator worked. Now I want, okay, I don't want the minimum value, I want the second index of that pair where the minimum value is the first one. So what can I say? I can just print this b. I'll get the second value. I'll get 20. So there you have 20. Got it? That's all about it. This is how you can play around with it. You can even use it in C++ in a similar manner. You'll have some function for priority queue, and then you can place whatever object you are interested in. If it is int long, then you can directly write it, or basically these pairs, pair, int, whatever, you can use it. Okay? Or you can even define a comparator. You can define a comparator here also. So that's it. I think coming back, let's solve this problem together. We are already halfway through the class, but after this it will be totally about problem solving. So we can finish it comfortably by 7:40 or 7:45. Please try to solve it yourself, and then we can have some discussion. Solve it yourself in whatever manner you can, and tell me what is the time complexity you are getting. So I want to see who can give me the best time complexity. What is the time complexity you are getting from here? So suppose this is an n cross n matrix. Okay, n cross n matrix. So if we do a basic sorting, if we say that okay, these are 4 rows, we need to club them. Suppose we club them together and we say okay, we will arrange them in this manner: 1, 1, 2, 3, 3, 4, 5, in this manner, 8, 10, and so on. Then if for k equal to 5, I can say okay, this is my value. What is the time taken for sorting? Now I think I'll wait for some answers. What is the time taken for this sorting? Given that this matrix is n square, if I just take all the elements in an array and sort it, what is the time taken? If you do the other way, that okay, I'll take this array, this is already sorted, then I will try to introduce this array within this, and then this array within whatever I get over there, and then this array within that, then that will take a long time. N log n, okay, that's interesting. Really? N cross n matrix, there are n square values over here. How many values are you sorting? You are sorting n square values, right? You are taking all the values in an array, there are n square values. So it is n square log n square, which is nothing but n square log n, right? This is the basic approach. This is a brute force. Am I right? Brute force of by sorting n square log n square, which is n square log n. Put all element in max heap and size of heap should be k. Maybe you need to think about it a bit. Why should the size be k? I don't see the size is k. Okay, max heap. Why max heap? Why max heap? Isn't it like we are searching for the kth smallest element? So, not really convincing. But okay, I hope everyone is clear about this brute force approach. Else, just ask me to explain, I'll explain this. I hope it is clear. We are just putting down into a single array, we are sorting it. What is another approach we can use? That okay, something like insertion sort. Take this array and push it into here, this array, so that both are sorted. Merge two sorted arrays. Merging sorted arrays means it is ordered m1 plus m2, which essentially means that it will ultimately become ordered how much? The total number of elements is n square. It will actually become n cube, something like that. N times will be merging. Every time it is about n square, so it is about n cube. We can't have that. No, we can't do in n square. If you just think about it a bit, it will be order n cube. Okay, Ranjan says because we need to find the kth smallest, we'll put all element in max heap and size of heap should be k. Ranjan, why I am not satisfied is that okay, for k elements, how many elements do you have to read over here? Suppose k is equal to 5. How many elements will you read over here? I know the element can be in this entire range. It can be this also, it can be this also, it can be this also, it can be this also. I don't know before reading it, right? Which is the perfect element. So I have to read all the elements, right? And then I can say that okay, keep on removing till I get something like that. Size of heap becomes k plus 1, pop the top and push the current element. Got it. Got it. Very good. Very good. But how many total elements do we have to read? What is the total number of elements we have to read? Do you agree that we have to read all the elements? We have to read all the elements, right? And after reading every element, you can do some operations. It will be something like this: order n square, maybe plus. I am not sure about this term, n square log k, right? Because k is the size of a heap. So whatever we were talking in terms of log n there, now we have to talk in terms of log k. So it is n square log k, right? N square is the number of operations, and there is the number of times when you emit the max element, the k plus 1th element. That can happen how many times? N square times. Basically n square minus k times, right? Okay, Devang has written a long one. Let's look into it. We need to maintain a min heap which will always store the minimum element of each row. Then pop the minimum element and push the minimum element, next minimum element not already in the heap to this popping till k times. Excellent. Exactly. Let me quickly cover the other approaches which are possible. This is the brute force. We could have tried something like this. That okay, we have pointers. We have pointers at these arrays. That okay, all are first starting from the way you do merge sort. When you do the combine step in merge sort, what do? We advance both the pointers in some manner. What we say that whichever is a smaller one, we advance it over there. Then if the left one is smaller, we advance it over here. Now here also we will do the same thing. We will say that okay, among these four elements, we will see which one is the smallest. How can we see that? Using a simple loop, we can see that okay, in these pointers, which is the smallest. So I see that this is the smallest. What can I say? That okay, this is the smallest element. Let my pointer move to the next position. Then I will look at these pointer positions. For pointer positions, which is my smallest? This is my smallest. So I'll move this pointer to this position. I've got my second smallest. For my third smallest, what will I say? That okay, this is my candidate, this is my candidate, this is my candidate, this is my candidate. So again, n comparisons, n minus 1 comparisons. So we can say that okay, this is going to win. So this is the third smallest. I will say advance a pointer over here. Then we compare it. 1, 2, 3, 4. Which is the best one? This one or this one, either of this. You can say okay, this one is the best. So you have got this as the next smallest element. Then you advance a pointer over here. Then you will say okay, this is the best. So you take this and this is your final answer. So can you see? This is a simple array approach that we are using where we are advancing the pointers. What is the time complexity? Time complexity is something like this. Every time you are going to compare n minus basically n elements. You want the minimum element. And wherever you get the minimum element, in whichever row you get the minimum element, you will say okay, advance the pointer from that to the next element. Right? You can think around it. This is exactly the same as the combined logic we use in merge sort. So the time complexity over here comes out to be n, order n every time. How many times? K. So order nk, satisfactory. Using these pointers, it will finish in order nk time. Pointer in each row and loop over them. Yes or no? This is not the optimal one, but make sure you understand this. This is a very useful approach, maybe very intuitive as well. What we are doing is first we are setting at the starting elements of every row. Then we are telling that all these elements, among all these elements, we will have our minimum element for sure. Wherever we have the minimum element, we will say that the candidate for the next minimum is the next element in this row. So keep the next element in this row and other rows keep them unchanged. Now compare all those elements which are currently in consideration and see which is the minimum. You will take order n time because there are n different rows. In every row you have one candidate element. So is it clear that we will get this in order nk time? Yes or no? Or do you want an example? Yeah. Similar to the merging k sorted linked list problem. Actually, I plan to do this problem, merging k sorted linked lists, later on in today's class only. But let us see how it turns out. We don't have too much time there, it's only half an hour left. Guys, are you understanding this order nk? Because if you don't understand this, it will be a problem to move ahead. Any doubts you have? Do you want me to re-explain it? Any doubts? Okay, seems like it is fine with all. The next another approach we can use is we can use binary search. Can one of you think how we can apply binary search? How we can apply binary search in this problem? We know that every row is sorted. So binary search always looks for that kind of a property where you can easily partition between the left half and the right half. So can you think of something where you can apply binary search? We can apply the technique of binary search by answer. Binary search by answer or binary search over answer. So we can say that okay, suppose that the kth smallest element is A. I want to see that which is the smallest A, which is the smallest value A, so that at least k minus 1 values are less than it. Okay? Or less than equal to it. So I want to find the smallest A such that at least k values, I'm sorry, at least k values are less than equal to it. That is what I want to find. So what can I say? Suppose A equals to 4. I suppose that I want to check for 4 whether 4 can have k minus 1 elements before this. So what can I say? I will do binary search in this row. I will say that okay, using binary search, this is the last element I can have. In this row I will have up to this row, up to this column. Over here I can't have any. Over here I can have all these. So I have 6 elements, which is fine. I can say that okay, 4 is a good candidate. Now I can search for less than 4. So let us say that okay, now I'll try with A equals to 2. A equals to 2. So let us see how many we get. Over here we are getting nothing, 0 elements. Over here we are getting 1 element. Over here we are getting 2 elements. Third row nothing. So we have 3 elements only, whereas k's value is 5. Got it? So yeah, this is how we can actually binary search over the answer, and we can end up at the final mid value which passes, something like that. What is the time complexity? Can someone mention what is the time complexity? There are n rows, every row has n columns, and the values can go up to, suppose, max val, something like max v. So what is the time complexity for binary search? So aij, that can go up to max v. K is less than n square, less than equal to n square, less than equal to 1, greater than equal to 1. And what else? N square values are there. What is the time complexity? For the binary search approach? No answers? The algorithm is clear, right? So what are we doing? How many times shall we do this operation of finding out in every row? Suppose once we do with a certain value of A. With a certain the value of a, what is the time complexity? It is log n in every row. It is log n over here, log n over here. So it is n log n, you can say. So this is n log n for every value of a. How many values of a should we take? Log of max v, right? So this is the time complexity. That's it. Yeah, right answer. So now let us move into the technique that Devang mentioned. We'll be using a heap now, and we'll be seeing how the situation betters. What shall we say? We'll say something like this. These are our elements. We'll use the same technique that we used in this approach, NK wala approach. We'll use the same technique. What will we say? First, put all these elements in the heap. First, put all these elements in the heap. Okay? What do we know? That our smallest element must be in one of these elements. We know that the smallest element must be one of these 4 elements, right? So, what can we say? Okay, by using a heap, store all these elements in a heap. So, in log n time, we can extract that minimum element. Suppose that element is this one. So what can we say? Okay, this is the main element. So now I am searching for the second minimum element. So which is a new candidate? These can be the second minimum. These can be the second minimum. This cannot be the second minimum. So I will remove this element. Whichever was the main element, I will remove it. And whatever comes after this, that can be the second minimum. So the second minimum must be one of these 4 elements. Does this make sense? Second minimum must be one of these 4 elements. That's the only thing. So now we can say that okay, from here we'll get the second minimum in log n time. We can extract that. Suppose this is the second minimum. So we'll get this into the heap. These 4 elements now will request the heap that give me the third minimum. Like give me the minimum currently in your place. So that will be the third minimum. Suppose there is a third minimum. So then this will get extended. In this way we'll get in some manner. Like the same approach we used over there, we are using over here. What is the size of the heap at any point of time? It is k. I'm sorry, it is n. What is the size of the heap? It is like from every row we have exactly 1 element, so it is n. And what is the complexity for removing an element? Every time we are removing 1 element. So what is the complexity? I'm sorry. So n elements we are storing, and k times we will be updating it. First we will be storing n elements, which you can say from n it can actually take n log n also. If you don't do the build operation in a wholesome manner, it can take n log n also. And then you will have k and k steps. Every step what will you do? You will remove 1 element, you will take the new element which is at the next. So it will be k log n. So this is your total complexity. Make sense? Make sense? This is your final complexity using heap, which is also the best complexity we are having till now, because k, we know k is, yeah, k can actually go to n square, but anyway, if k is less than n, then this is definitely the best algorithm. If k is not of the order of n square, then you can say that this is more reliable, right? Like if k is n square, order n square, then this is more reliable. This n log n multiplied by log max, right? So it depends on the value of k, what kind of an algorithm, how good this algorithm is. If it is given that k will be less than 100 or less than 1000, then okay, this is the best algorithm. If n is less than equal to 10 to the power 5, or maybe, I don't know, anyway, something like this. We can use binary search, yeah, definitely. The thing that we discussed just before this. Cool. Before we finish, there is another important thing. What is the extra space we are using? Over here, In the brute force technique, what is the extra space that we used? Order n square. Order n square extra space. We are pouring everything into a new array. For this technique, what is the extra space that we used? Nothing. We did not use any extra space. No extra space, or basically order 1 we can say. Just the pointers, okay, for the different rows. For the binary search, what is the extra space? Again order 1. No extra space, order 1. Over here, what is the extra space? It is the size or the space occupied by the heap. So that is order k. Got it? Clear? And yes, the algorithm is best for smaller values of k. Cool. So if everything is clear, then let us move to a new question. This is CodeChef IPC Trainers. CodeChef IPC Trainers. Read the problem. It is a short problem. Read the problem. I did not implement the previous question. If you have any doubts, by the way, how should we understand that whatever is the minimum value, in which row it is lying? How can we understand that this minimum value is in which row? We can store it in the form of pairs. In pairs we can store it. The value will be the first element and the second element will be row number. So from there we can get the row number. What we can say is that remove that element and in that row number go to the next index and enter that element. That is something we can do. Okay, and whatever is the current pointer for each row, we can store that separately we can store that okay, in this row this is the current pointer, so we can do it very easily. So here also think what are the different ways in which we can analyze. The space for heap will be ordered n. I'm sorry, okay, so I thought that k is the size of the heap. I'm sorry, so yeah, exactly. This is order n. Yeah. So whatever, how many elements you are storing in the heap, that will be the time complexity. So, sorry, space complexity. So here it is order n. Thank you. Thank you for pointing out. It's order n, definitely. I'll quickly, okay, read the problem, then we'll look at the constraints. Remember, suddenly if we want to access any element, that will be ordered n in a heap. You can't suddenly ask for any index. You can only ask for the minimum or maximum. So think in that terms whenever you're thinking with heap. You can think any data structure over here. Don't use a tree set. Okay. Okay, I hope you have read the problem. So N and D are both within 10 to the power 5. What is D? The number of days when the camp will run. The total number of people are 10 to the power 5 trainers basically. And yeah, that's how it goes. DI is the day on which he will come. TI is the number of lectures he wants to take. SI is the sadness increase level, whatever we call them. Okay, and SI is also upper bounded by 10 to the power 5. TI is upper bounded by D, and it's fine. Okay. So read the question. I'm coming in a minute. If you have any questions, just put down in the chat. Yeah. Just put down in the chat. Okay, so have you thought into it? Have you reached some answers or any approaches? I'll explain the question for you. There are N trainers. The camp will run for D days. Up to here, everything is fine. Now, every trainer has got his preference, or you can say like rule. He will be coming on this day, and he will be staying till the end. So you cannot assign his lectures before that. You have to assign it in that duration only. This is an advantage that he will stay till the end, as the problem would have become tougher. So now he will stay till the end means on every day you have a set of people. On every day you have a set of people who are currently there, and with days that may increase, that may remain same, depending on which day they come. So given that every day you have a certain set of trainers, which trainer should you choose? Which trainer should you choose for giving a session? Because on one day you can have at most one session. You may have 0 sessions also, but at most one session you must have. on a single day. Which session, which trainer should you choose? Any answers? That's weird. Are you not following? Or am I not receiving the messages? कुछ दिक्कत हो रहा है फॉलो करने में या लाइक मैसेजेस दिख नहीं रहा मुझे? Like guys, try to be as interactive as possible so that we can cover more and more problems. Because adding a session is not that feasible. It always means that there is a change in the schedule and yeah. So I understand that writing every time is not that easy. And you all might be trying to do something on your own, you're not sure about your approach. That might happen. But this is a very objective question that I've asked, which is that on a particular day, if k different trainers are present, which trainer will you choose? Which trainer should you choose to offer the training? There are two things I want to check over here. How you choose among them, and how do you decide which trainers cannot deliver sessions whom you cannot assign it. There are these, like you can say, one thing, single thing that I want to check. It has got nothing to do with the heap or whatever we have discussed. It is rather a more general question. If you know this and if you are expert in implementing heap, you don't require to be in this class. At least for this question, you don't require to. On a particular day, you have some trainers who have got their own statistics. You know their statistics. What is their SI value? What is their TI value, DI value, whatever are there. Now, whom will you assign the session? This is the question. So what do you think? Whom should you assign the session? I mean, are you finding it difficult to follow, or is there like, are you finding the basic conduct of the class to be quite difficult or boring, or maybe not up to the mark or something? Or you just want me to speak at this time, later on you will rewind and see what are going on. You will see the recorded content. Is it so? Whatever it is, I have been from your time, but anyway, I have not been attending classes for DSA. And anyway, we had online classes only in our colleges, and that used to be a bit different. I know you have, all of you have come here, right? Thank you. So Vijay has given like the correct answer. I was just expecting another thing, but okay, it is better than nothing. So see, in college we have attended many classes because we had to attend it. I think no one is an exception in my college or in any college we can think of. But over here you all have come voluntarily. So try to utilize it in the best possible manner. And help me, help you in the same. Okay. So coming back to the point. Who has the largest sadness value? Yeah. So whoever has the largest sadness value, we should choose that guy. Why? The first thing is, if we think that okay, if we choose that guy, then maybe somebody else we cannot choose who may not, like, we could have chosen this guy later on, but now because we are choosing him, we cannot choose the other guy, something like this. You can think of something like this. But it turns out that since all are staying till the end, by utilizing him now, you are not wasting anybody else's opportunity. You can utilize the other person the next day in case you feel necessary. So definitely one who has the highest sadness value, you should try to cover up that. Why? So that now whatever SI values you have to endure, basically what do you need? Every day when a certain trainer is not able to teach, you need to add his sadness value. So you have to add something like this. Suppose there are certain number of trainers. You have a trainer maybe I1, trainer I2, trainer I3, trainer I4, something like this. Okay, I3 and up to trainer IK. Now if you say that okay, one of them I'll be assigning a session, what does this mean? You can say, leaving this, the rest will be your total sadness on that day. So yes, by using this greedy approach, what we can ensure is that this SI3 won't happen. Basically, he won't have to deliver a session over here. All these things will suffice. Basically, the remaining sum will prevail. So we should remove the largest one so that the remaining sum is the smallest, right? This sum, including this, we should remove the largest thing so that the remaining thing is the smallest. Let me look at the question once again. I'm sorry. So what has been said is whichever lecture he has not been able to teach. So it doesn't mean on a per day basis. So it is not on a per day basis, but on a certain day, if you have so many different people who have their lectures remaining, which lecture should you assign? Whichever trainer you know has the largest sadness value, जो भी तुम्हें पता है कि सबसे ज़्यादा दुखी हो जाएगा, तुम उसी का असाइन करोगे ताकि like जो सबसे ज़्यादा बोझ है वो धीरे धीरे हट जाए, something like this on a per day basis. If you say that no, this is smaller, still I will assign this one only, then what will happen? Later on you may face a problem. So by greedy algorithms and by the proofs of greedy algorithms, which believe me are quite boring at times, you can prove that this is always the best approach. What will we say that जो भी जिस दिन सबसे ज़्यादा नाराज़ हो जाता है, हम उसी को उस दिन सबसे ज़्यादा satisfy करते हैं. Rest we'll see accordingly, successively. Okay, something like this. So where are we now? I see. Another thing is there. Cool. Now this is another thing you should remember, that a trainer may be present, but maybe all these sessions are finished, all these lectures are finished. So in that case, you should not take that lecturer into account, that trainer into account. You should take that lecturer or that trainer only when some of his lectures are left. When you can say that okay, whatever number of lectures are left, remaining lectures, whatever is that is greater than 0. You should have that checking. So if that is not there, then you should leave that. You should not consider that trainer not only on this day but also on the upcoming days. You should remove it completely from whatever data structure you are using to keep track. Got it? So combining what Vijay said with the last point that I mentioned, what essentially we want is every day we want to know who is the lecturer, who is a trainer with the maximum sadness value and whose number of lectures, remaining lectures, is greater than 0. Right? Up till here everything is fine. CRCT, I'm not getting, you have written previously as well, CRCT. CRCT? I'm not aware of the full form. Maybe it's a very common one, I don't know. Okay, cut now. Fine. Cool. So now the thing is, every day you are getting new trainers. So from the first day to the last day, if you have to read through all the trainers to see that okay, on a certain day D, which are the trainers who are available. So I have to look at all the N trainers and I have to see that okay, is your DI value less than equal to D? If your DI value is less than equal to D, then yes, otherwise no. Something like this. So in this way we have to take into account, okay, if it is yes, then see what is the SI value and what is the TI value, all these things. But again, like what is the time complexity? If we just say that we'll read through all of them, what is the time complexity? Number of days, which is d, multiplied by number of people, which is n, which is a lot, 10 to the power 10. We cannot definitely use this. So what are we left with? So we are basically left with something like this. Where am I? Yeah. Uh, we should arrange these people in a manner so that I can say, okay, first these people are coming, next day these people are coming, next day maybe none of them is coming, then these people are coming. In this way, we should first arrange the people. So we can first sort it, and there is a kind of comparator sort by which we'll be getting that, okay, on which day which are the people I'll be getting that by comparator sort. Then what we can say is that, okay, now on every day I can read through this part. I can say that, okay, I've read up to here. I will check how long I can go from here, which people I can include newly to my team. I'll include them, and on every day, once I've included them, what do I have? I have a set of people with their SITI values, basically which specifies what is the SI thing, the sadness level, and what is the left, what is the number of days left, basically what is the number of lectures left. So I can say that, okay, if Li is greater than 0 for a certain number of trainers, and among those trainers I'll choose the one which will have the greatest SI value, and I'll reduce its Li by 1. Got it? This is something that I'll be doing. Now what data structure can I use for it? Can you see that I can directly use a heap for this part of the purpose? That find me the maximum value. So I can directly ask my heap, okay, currently you have some elements, what is the maximum value? Then I find some new people have come. So I'll say, okay, add them over there. Then suppose it happens that, okay, I have emitted some element, I've taken the top of the heap, but I see that, okay, Li value is 0 over there. So what should I do? In that case, I should say, okay, discard it. Look for the next element. If the next element you see that the Li value is not 0, then okay, then you're done. That is the maximum element. So can you see that stepwise it is absolutely linear after this, straightforward. Does it make sense? You can use your abbreviations or whatever you feel comfortable with. Let me know. So what are we doing first? We are sorting the people on the basis of the dates they are coming, and then day wise we are proceeding. Suppose let us take a test case. Let us move this desktop over here. Okay. So 3 to 3, 1 to 300, 2 to 300. What does this mean? DI, TI, SI. DI, TI, SI. So 1 to 300, 2 to 100. 1 to 300, 2 to 100. The first one was DI, next one was TI. So DI tells that, okay, he comes in the first day, he comes in the second day. So they are already sorted by these things. So now I can say that, okay, on the first day I have one guy whose sadness level is 2. I'm sorry, whose sadness level is 300 and whose number of lectures left is 2. I don't have anybody else. So now what can I say? I'll remove only this. This is the only guy I have. So I'll be removing this. I'll basically be reducing its number of lectures left by 1. And then what do we have after this? We have one more element in the second day. These are the elements I have. I have 300, 1. And I do have 100, this has 2 lectures left. Now whom should I prefer? I should prefer still this one. So I'll say, okay, now reduce it to 0. Got it? I'm sorry, I drew it over here. What I basically drew over here is something like this: 300, 2. I just crossed it and wrote a 1. Why? Because it is getting reduced from 2 to 1. So what is the total thing? It is what is the total sadness level? We have utilized this. This is 300, 0. But this one we could not utilize. What is number of days? Let us look at it. Total number of days is 3. Is it? Okay. So next day we will again look at it. Next day we will see that, okay, we have 301. So we can say I'm sorry, we don't have this. We have this one. We have this one left. We have 102. So what can we say? That okay, reduce it to 1. So now this is the only thing left at the end. So we can say that the only sadness is 100 now. Let us tally it. The only sadness is 100, right? That's it. Even if you are asked that okay, on a per day basis, you have to say that okay, on the total period, what is the sum of the sadnesses, such that every day a trainer cannot give a lecture, he will be unhappy about it. Every day the trainer cannot give a lecture, he will be unhappy. So over there also you can do in a similar way. Nowhere is it different. Absolutely similar. So do you have any questions around this? I'll stretch this class up to about 7:45 or 7:50. I'll shortly discuss HeapSort and then we'll be calling it a day. Okay? Cool. Let us do that. So what is HeapSort? Something that I was actually explaining in the beginning of the class. If you have to, suppose your array is inside a heap, all your elements are inside a heap, and now you want a sorted version. Suppose there is a question which says that do these heap operations, and then it will say that okay, whatever elements are currently existing, give me the sorted order, give me all those elements in sorted order. So what will you say? That okay, in a heap this is what I can do. Always remember, in any question, those are the only 3-4 operations you should be doing. Build operation, insert operation, find the minimum, delete the minimum, that's it. So using find min, what can we say? That okay, this is the minimum element. Now I can say okay, delete the minimum element, then whatever is the next minimum, that will come to the top, that will become the new minimum. So we will say okay, do the delete minimum over there, or extract that minimum. So then we will gradually keep on getting this extract minimum, and eventually we'll be forming our sorted array. Is this convincing? If you have a max heap, it will happen in the opposite manner, you will have the reverse sorted array. Make sense? That is exactly HeapSort. So it is a heapification process which takes like n times heapification. That is what takes the time. It is order n log n. Every time when you are fetching the minimum element, it is order 1, but when you are removing the minimum element, it is followed by a heapification which is order log n. So any questions around this? So I finished it in a super fast manner. If you have any questions, you can ask. Else I will give another question. This is probably the last class we have on heaps, and the next day we'll have some problem solving on heaps, on segment trees, and on tries. So before I finish, maybe you can ask any questions that you may have. This is one question that okay, we won't hurry, we can take it in the next day as well, but maybe we can cover it. Okay, on HeapSort specifically you won't find any questions. If anybody asks you, HeapSort has these characteristics. Is it stable? What do you think? HeapSort is not stable. So if you have equal elements, you don't know absolutely how will that get stored, okay? Unless you prepare the comparator in that manner, it is not stable otherwise. What else? Is it in place? Yes, it is in place. In the heap only everything is taking place, so it is in place. And what is it? It is optimized, it is order n log n always. This is the worst case, this is the best case, this is the average case. It is order n log n, okay? And also this is the internal implementation in some languages, in some libraries, okay? These are the properties. So you can compare it with merge-sort, quick-sort, and these things. Other than the heap, there is no extra space which is required. So what is the total space required? For the heap, there is an order n space required. In merge-sort, what is the total space required? It is order n log n. In a merge sort, you require a total of order n log n space. I hope you remember. Order n log n space. If you try to do it in place, then the time complexity will deteriorate, right? Then the time complexity will not remain the same. Cool. So this is a question. It's a kind of a theory question, so it's good to cover it. Given k-sorted linked lists, I'll not be going into too much of detail. I'll just be sharing the idea and we'll be closing the class with that. If you have any questions, you can ask. Given k-sorted linked lists, merge them. So here also the idea is the same. Whenever you're merging any two sorted linked lists or two sorted arrays, we use the combine function, right? So if you are merging k-sorted linked lists, you can use the approach we have used in our first problem. So what can you do whenever you're starting the process? What can be your first node in your sorted linked list? It can be either one of the, like it can be the first node of either of the linked lists. Whatever input linked lists have been given to you, from either of them, the first node will actually form the first node of your answer. And when you see that okay, that we are going to take, advance it over there. What you are going to say that okay, this one we are taking in our answer. This is our next minimum. So you can take that okay. If this is node, then node dot next is going to be the next element in the heap. So you will tell that node dot remove this particular priority queue dot remove whatever is the minimum. You will say priority queue dot poll, and then you will say that okay, now I want to add this, like I want to add the new element. So you'll say that priority queue pq dot add node dot next. Okay, that's it. Next time when you fetch something, you will do something like this: node equals to pq dot poll. Got it? This is in Java. In C++ also it is quite similar. What is the time complexity? Pretty similar to the first question. We have if all of them are of size n, if there are there are k sorted linked lists each of size n, then what do we have basically? Kn log k. Got it? So if you have to do the sorting together, you will actually face kn log kn. We have bettered it from kn log kn to kn log k. Okay. I hope it looks fine. Any questions you have before we finish? Or do you have any issues with anything I discussed in the last 10-15 minutes or in the whole class? Anything you want me to come over that again, or ask any doubts, maybe present something which you have seen somewhere else, or okay, this was different in that platform, in that website? Anything? So yeah, I won't take any newer problems now. I had 2 more problems for today, but we'll do that on the next day, or we'll basically see how we figure out things. Okay then, so if you have no questions, maybe we can call it a day. I hope you got something interesting today. I hope whatever you learned today, you will be able to implement it directly in the problems. I do hope that after this class, you will be trying some implementation and trying some easy problems. Especially, you can submit the problem over here in this website, and you can see if it works. If you have any doubts, you can ask me in the next class with your implementation, or maybe with the basic idea. We can go over it. Next class will be mostly on doubt clearing and problem solving, and we will brush up all the topics that we have covered till now. So yeah, till then, take care, keep coding. Last 1 minute. So can you give intuition of trapping rainwater in matrix? I have a total video. You can actually find on the CodeChef channel only. You can search for the problem, trapping rainwater problem. I think I took around 1 hour in explaining that, because there were I think 4 approaches. I don't remember exactly. So intuition wise, it again depends on which approach we are following. I think there were two good approaches, so you can look at that video. There I had explained everything in detail and all the intuitions I had explained in detail. Okay, I spent extra time on the intuitions. If you have any doubts, you can come later on. Make sense? Alright then, take care, keep coding. Uh, Trapping rainwater in matrix. Oh, acha, I just mistook it. The problem that I had discussed, I think it was trapping rainwater in a line, like among bars, in a histogram kind of a thing. In a matrix, okay, well, that may be a different problem. In that case, cool. Uh, okay, I don't remember the problem exactly, but I can get the idea. You have this kind of a matrix, and you have the heights over here. Then in a particular cell, you need to, like, you're asking what is the amount of water that can be stored. So at every node, first of all, you have that easy thing, right? You know what is the previous greater, and you know what is the next greater. Not the previous greater and next greater. You actually know that single thing. That what is the something like this. Uh, so it is just escaping my mind. Uh, if you have two over here, and if you have I don't know, if you have three over here, if you have five over here, then it can ooze out. Like if you keep four over here, then it can ooze out from here, right? So I have to see the actual problem statement. I think I need to see that. Basically, the intuition is that around it you need to find out whatever are the heights. You need to find out the minimum height. That minimum height will actually dictate how much water you can save here. Another approach is that which we followed in case of a linear. In case of that linear version, what we said is that if you are at this particular point and you are at this particular point, then for all which are in between, you will follow this one and this one. You will actually like move towards the between, and you will keep in mind what you have at the two different ends. That is a different approach. But anyway, let's take it on a different day, I think. So yeah, any more questions? Else, I think we can call it a day. Good luck. Keep coding. Bye.